This is an amazing session coming up. Rolling with the Patches is going to be handled by Janmejay Singh, a hacker at heart. Janmejay is deeply interested in distributed systems, performance scalability, and all sorts of hard technical problems in general. He has his head buried in the metadata store at Rubrik these days, wrangling the problem of disruption free upgrades in their backup and data management appliance cluster. Before this, he was with the infrastructure team, shared technologies group at Flipkart, and was responsible for solving some interesting challenges to help many services scale to power the amazing big billion days. Ladies and gentlemen, presenting to you the amazing Janmejay Singh.
Hi everyone. Just waiting for the audio video to be confirmed to be working good. All right. So welcome to this talk. This is about enabling rolling upgrade on a fast moving product, and this is about the CDM stack of Rubrik. Rubrik is no, is known to be one of the most respected providers for backup, restore, with storage tiering, things like DR to another data center or to cloud, orchestrated application recoveries, and things like ransomware detection and security. We're getting more and more into the security side of things. So we are also getting into data compliance, governance, and things like that. So that's Rubrik for you. And above all, we value simplicity. When we entered the market of backup and restore, the existing products uh, were not something that the customers could use themselves. There were complexities around configuring the product. There were complexities around using the product, maintaining it, and so on. And Rubrik has really changed the game there. So simplicity is something that we view as one of the most important things that product needs to have. So that's us. We're talking about rolling upgrades in the CDM stack. CDM stands for Converged Data Management. And this stack, it primarily runs on clusters, sometimes virtual clusters, but in 90-95% of the cases, it's physical clusters. And these clusters are realized over multiple different types of chassis, but these are basically in a data center, and we use a masterless design and a distributed file system to get an aggregate to get the storage aggregated so that the backups can be stored on that and retrieved from anywhere. And we perform things like local storage of backups or archival of backups or replication of backups to another data center or to cloud and things like that. And the backups are SLA driven. And an SLA would typically be expressed as I want to retain one backup an hour for the first 3 days, and after that, just one backup a day for the next 7 days, and then after that, just one backup a week for the entire year, right? So that's what an SLA would typically look like. And there's continuous data protection where we are just streaming the data into the Rubrik cluster, and that is the backup, right? So this is the backup side of things. Of course, there's restore and other things, but we are not getting into all of that because that's not relevant to rolling upgrades. This is just to give a general idea of what the product is like, right? The CDM stack is primarily written in Scala. There's a lot of Scala code that deals with things like backup jobs, restore jobs, indexing of the data, being able to show you what files are there in a backup, being able to retrieve a particular file or a directory and things like that, and being able to express what to backup, what not to backup, what is whitelisted, blacklisted, things like that, or configuring SLAs that control these jobs. So for all of these things, there are REST APIs and the data services that allow our clusters to talk to each other. So a cluster might need to talk to another cluster, another data center to replicate, or it might need to talk to, say for a VM backup over VMware, it might need to talk to the vCenter. and acquire the information about VMs from there, and then perform backups with these VMs. So there is server-side integration that is primarily written in Scala, and there's archival, which is over a period of time the backups become less relevant, and we move it to cold storage, and that could be on the cloud, or that could be in a cheaper storage array on the inside the data center, owned by the customer, and so on. So all of this logic, the meat, is written in Scala, or the smarts, if you will. The C++ side of our product, it deals with primarily file system and data representation. And data representation involves how the backup would be laid out on storage and things like that. And then what are the relationships between the first backup, which is often called a full backup, and the next backups that happen after the subsequent backups, which are increments. So we would back up whatever changed from the first backup and things like that. So things like these, they need to be represented on the storage. So they need to be represented as files, or the data inside files, compressed using various algorithms, checksummed, and deduped, and things like that. So all of the data path components are written in C++. There is Golang. The metadata side of things is quite Golang heavy, and that's what we'll be getting into today. So the metadata services, the services that provide access to metadata, that provide APIs for accessing metadata. The metadata here is everything, including the path, the files, the attributes of files, the sharding of files, its erasure coding, where are the stripes being stored, and things like which backup is referring to a disk, and which other backups are referring to the same disk, and things like the backup, how many disks does it have, or which VM does it belong to, or what is IP address when it was being backed up. All of these things are metadata, and metadata services are written in Golang. And there are a bunch of installation helper scripts, or maintenance helper scripts, and things like that are written either in Python or shell script. So that is the the kind of spread of languages. There are other languages, of course, but these are the main ones, right? The CDM cluster can either be 4 or more nodes. It is usually the most common chassis, is 3 dense spinning disks, either 4 TB or 8 TB, and one SSD card, where our root partition and our metadata partition, and an SDFS, the distributed file system cache, and things like that, they all live in there on the SSD card. And it has a 10 Gbps network, and it runs a bunch of services. These services would start at the API layer, and the data services that move data around, or the data path services that encode, decode data, that store data, make sure that we have sufficient level of redundancy to tolerate failures, make sure it is consistent, and things like that, right? And there's distributed job runner, the jobs that provide us as backup services. They read data and store it in either archive or in the local storage of the distributed file system, and things like that. The distributed file system itself, which is essentially like a POSIX file system to the rest of our components. And below all of this goes the metadata gateway and metadata store, because the file system needs to know about its files, how the files are broken up, the kind of things I mentioned on the previous slide, where the data is, which node has which part of which file, and things like that, right? So metadata is kind of the basis of all of this, and all of this requires metadata to be consistent and available for rest of the thing to work correctly, right? So there is a lot that happens in a rolling upgrade, and it really depends on what is being rolling upgraded, right? There could be things that have separation of data and control plane, and control plane upgrades, and then so it's pretty complex data plane upgrades, even more so. And what we are talking about today, in this case, there's a lot that goes into it. There are things like IP failovers that need to happen. There are the NFS shares that need to be failed over. There could be SMB shares, CIF shares that need to be failed over. and files need to be moved around to make them available across restarts and things like that. So there's a lot that happens, but we are only going to talk about metadata. Why metadata? Because all of the things that I talked about, they have some structure to it. When you're failing over an IP, there's a way to do it. After you fail over an IP, you need to have the service that is supposed to receive traffic that's supposed to receive the traffic for the component that was running on the IP address previously, right? That service needs to be up. It needs to be listening. It needs to accept connections. So there's a way to do it. There's a method to madness, right? But for metadata, there's no method to madness. It's just queries, and the queries need to be responded to. They need to be answered, right? When somebody fires a select, the response need to report. It needs to report rows, and that's it. There are no rules. Right. So the way the our metadata stack works is there are two homegrown ORMs. Well, there are the three actually. There are two in Scala and there's one in C++. We are primarily we were primarily a Cassandra-based product. The product was written around Cassandra. Well, not written around Cassandra really, but it was written to work with Cassandra to store metadata, and metadata is very central to this. So in that sense, it was around Cassandra, right? So the ORMs talk Cassandra, they talk CQL, right? Cassandra querying language. And there is a new ORM that talks SQL, and we'll get into that a bit later in the talk, right? So we have replaced Cassandra since because we ran into a bunch of correctness issues that were fairly fundamental to Cassandra design. They were not bugs; they were the design flaws, right? So continuing down that path, expecting consistency, meta is sacrosanct in this case, right? And expecting consistency was kind of a natural thing, and losing consistency was not acceptable, and that's what was happening in a lot of cases. So we moved away from Cassandra, and the way we did it was we wrote SQL proxy. It's an L7 proxy that talks SQL. Applications talk to it. It talks SQL, and then it translates SQL to SQL, and it performs a bunch of structural transformations, and then issues PostgreSQL queries to the lower layer, which is realized by CockroachDB, which is a distributed database. And we run a patch version of CockroachDB. We have a bunch of things to make the clocks more reliable. We have a bunch of things to make sure that we achieve the desired level of redundancy, and we can tolerate a desired number of failures in extreme conditions, and things like that, and a bunch of telemetry and stuff like that. So there's a lot of change that we have made on top of CockroachDB, and that's what we run. The metadata is it kind of consists of about 420 tables, and there are some primary ones that have a lot of data, and then there are a lot of other tables that could have a few thousands to a few tens of thousands of rows, right? The bigger ones can have several million rows, right? We have all sorts of metadata, and it's usually less than 62 GB of metadata on each node. So for a 4-node cluster, we basically have 4 partitions that are on 4 different nodes. Each one is 62 GB, and that's where the metadata lives, right? On larger clusters, we could have a lot of nodes, right? So what's the problem with rolling upgrades? The problem is that we need to evolve the table definitions. We add more features. For that, we might need to add columns, add new tables, build new relationships between columns of a table or across columns of different tables, and things like that, right? And it's a fast-moving team, and there are things that come up in the market, and we respond to those things by building features, enriching the product, and this happens very, very rapidly, right? And for rolling upgrade, all of this needs to work together: the new features, the old features, the metadata, representation of the two. It all needs to work together, right? So we had a bunch of choices ahead of us. We could have chosen to pre-plan forward compatibility. So basically write code in the previous version so you can write code in the new version, that kind of thing. But what happens when you realize that you need a new feature and you haven't written code for it in the previous version, right? So what do you do in that case? So it hurts velocity. So you have to basically wait until the next release so you can release the forward compatibility, and then the release after would actually bring the feature into the market, right? So it reduces flexibility. It's a massive departure from the current model of schema evolution, where people just evolve their schema following a spec, right? And when the release gets deployed, it's the new schema, it's the new metadata, and they make progress from there, right? So it would open up room for bugs, because what if people forget to write forward compatibility correctly, right? And the complex restrictions on schema changes, and we could have put a lot of restrictions and said, all right, you can do this, you cannot do that, and that would once again affect velocity, and it's very hard to enforce. You can ask someone not to add a column, but how do you ask someone not to change the data that goes inside the column, right? What kind of verification do you need? You need to support something like that. So this doesn't scale, and it can corrupt metadata when these things are not caught early on, right? So there are basically two major questions in front of us. So the semantic changes to metadata, how should they be managed, right? The old services and the new services, they need to talk to the same metadata, the same set of rows at the same time. So how do we make sure that they both see a consistent view of metadata, right? And how do we migrate this metadata? So all of the metadata that is on the cluster is old at the point when upgrade starts, but by the time upgrade is done, it should all be new. So how do we achieve this, right? So we considered a lot of designs, and in the interest of time, I'll not get into the details of this. I can, of course, answer questions if you have any at the end of the session about this. But basically, we considered a bunch of different designs. There were trade-offs around cleanliness, around how flexible the design is, how fast does it allow us to move, what kind of restrictions it needs, and the kind of just pure technical complexity of implementation, right? So there were all of these things on the table, and the effort involved, of course. And what we did was we labeled our access sites, right? So of course the query in application doesn't look like this. It's not. This is a SQL query, right? It is generated from the way you access the ORM, and we created a concept of labels, and the labels are basically use case identifiers, right? So there is a namespace in the label, the label namespace LNS, right? So it tells us which component, and this identifier LID, which tells us the use case. So in this case, I know that the select is being made by blob store for adding a new content, right? And then there are other cases like insert, where the data has been inserted by blob store in order to create a new group, right? So these labels basically are use case identifiers, and by looking at a label, you can tell which use case has triggered this query, and from that you imagine a mathematical setup where you have a domain which is the labels, and the effect. So this becomes a bijective function, right? Each label has a particular effect that it has to achieve, and you could make it subjective, if you wanted to, but we have bijectivity at disposal, right? And then what we did is we let component owners, say the owner of the job service, right, write label handlers. Now, what does a label handler do? It allows us to atomically switch from old to new semantics, right? Intercepts access, and on the intercepted access, it can choose to do whatever it wants. So the user wants to insert ID and the value of the column foo in the table bar at this point, right? But we can choose to split column foo into two columns, say foo1 and foo2, right? And half the data goes to foo1, half the other half goes to foo2. And there could be any number of reasons why the component owner might want to do this, and this would allow them to, say, break columns into two separate semantic columns, or add more data to the column which is not visible to the application, to the old application, but it will be used by the new side of the application, and so on, right? So it allows us to transform the data that we insert over here in this insert statement, or transform it in the select statement, right, before we return it out, and read it from multiple places, do scatter gather kind of queries, and so on. So we return the expected results from the label handler, and that's what goes to the application. That's what the application would see, and we do not engage these handlers on nodes that are running the new code, because they already expect new semantics. And at the time of upgrade, we just load and engage the label handlers. And that is how we handle semantic change. This is what SQL proxy really looks like. We are going to be focusing on a small part of it for lack of time. Right? So we're going to be focusing on what is the label handler, what does it do, and then how a little bit into how do we migrate the metadata. The two questions that I asked, right? Now the label handlers, or LH for short, is basically semantic translator, right? What it does is service owners can register the semantic translations for any changes they make. Say release 6 is out in the field, release 7 is about to hit the field. In release 7, I built a feature that needs to use the same table that release 6 uses, but it needs to use it in a new way. It has a few new columns, right? So my label handler for release 6 access of the table would basically make sure that the data is consistent between the new columns and the old columns, and would make sure that when the old side updates this data, it doesn't break consistency of the row, or it doesn't break consistency of the data model in general. It could be beyond the row. It could be multiple rows in the table. It could be multiple rows across multiple tables, right? So LH is hooked up and engaged when we are processing a query. The query tells us which label. The label tells us with which handler. We load up the handler and we engage the handler, right? And it performs semantic translation and it uses LSP, which is load store primitive, right? As the name suggests, it is a primitive. It has no semantics of its own, right? It powers access for both version X and version Y. You ask for foo, you get foo. There's no transformation going on, right? So this is what the interface looks like. We can look at what the update label handler looks like. Right, so here in this label handler, we pass the label in for additional context. We know the table that we're operating on. We know the assignments that we're trying to do. We know the conditions for the query, and we know the atomicity conditions in the if cond, right? And then you can see a similar API in load store primitives, which doesn't care about the label because, like I said, it doesn't understand semantics. It does no transformations. You ask it to execute an update, it executes an update. That's all. So a label handler would use the LSP and would actuate the update, but it can perform arbitrary semantic transformations before it actuates the update. The very simple being identity, which is you take whatever's being passed over here and pass it into LSP. Of course, that would work, but why would anybody want to do that? Um, uh, the more complex ones would be some transformations. For instance, the query is to table foo, but I know that after upgrade, the table foo is going to fall out of favor. So I need to query table bar, right? And although the column that is being requested is column A, I need to return the column B because I know that the data that was in A is now in B, right? So that kind of transformation happens here in the update handler. All right, so this is what we did. We have a node on the left-hand side. We have a node that is not undergoing an upgrade, right? The file system, there's job runner, there's API, there are a lot of other services that are talking to the SQL endpoint. The SQL endpoint is issuing labeled queries to the base LSP, and the base LSP does not care about the label, so it just operates on the query and returns the results or actuates the results for updates and inserts and so on, right? When an upgrade is in progress, what happens is the labeled queries are still coming in. These services haven't restarted. The node hasn't restarted, right? So file system and job runner and everything else that is talking to the SQL endpoint is not restarted as part of this, right? They still continue to talk in terms of version X semantics, right? And they talk to the SQL endpoint, which issues a version X semantics call, which ends up talking to the access LSP. This is where the label handlers are used, and this transforms the query to semantics Y, which is the new semantics, right? And issues an unlabeled query to migrate LSP. And migrate LSP says, oh, all right, this row requires a change. So it runs the change first, right? Say in my foobar example, the column has been renamed and the row needs to go to a new table. So before it allows access to that row, it would first migrate the row. So the row would disappear from the old table, it would appear in the new table, and then the access would go through, right? And this blue axis is the new semantics, right? Now we are going to access table bar because the table foo is gone. And the base LSP does not have any semantics. Like I said, it issues the query to distribute metadata store and returns the response, right? State of an upgrading cluster would be something like this, where the first diagram on the left side is the same that we had a look at on the previous page. And the one on the right, it shows us a node that has undergone a restart. Sorry about the incorrect version here. This is this file system version Y and job runner version Y, and everything on this node is running version Y code. We are upgrading from X to Y, Y being the newer version, right? And then they're issuing these labeled calls to CQL, except there's no label handler because we are on the correct semantics already, so no semantic transformation needs to happen. So this is what an upgrading cluster would look like. There would be multiple nodes at version X, there would be multiple nodes at version Y. Orchestrating all of this is done through a state machine like this. We will not get into the details in the interest of time. But basically, what happens is we have a quiescent state here where we perform semantic switch from version X to Y, and thereafter all access to metadata is version Y, right? And in the end we apply cleanup. So we made structural changes here and in cleanup, and once cleanup is done, we're kind of on the new state with all of our metadata, right? So we had the choice of language to make. We could have chosen Golang, which is what SQL proxy is written in, but we chose to build this in Scala because it is where meat of our logic is. It is easier to manipulate data in Scala with functional primitives, right? And it is neat because there's no forward compatibility constraints. All the compatibility code goes as part of the release, right? We use Scala for label handlers, for metadata change, the thing that we didn't talk about, and it unlocks parallelism with neat futures based API and so on. Right. The learnings and takeaways from this is evaluating the solution space exhaustively. Right. There were a lot of trade-offs to make here. Golang versus Scala. There are multiple complexity trade-offs there. There's shared memory versus separate process. Should this whole stack that we're talking about here should this run as part of shared memory in SQL proxy process? Or should this be a separate process? Obviously, there are simplifications with a separate process, but there's performance overhead. There's GNI versus protobuf, or protobuf and gRPC. There's CQL versus SQL, and there is some value about data-driven decisions that I'll talk about in the next slide. And feel free. You kind of learn to make choices for the path less taken more freely, right? And the most important lesson is evaluate your base capabilities that you want to build in a product on day zero very, very carefully. If you want to build rolling upgrades, then think about it from day one or day zero rather, right? And avoid tech stack fragmentation. I talked about an SQL ORM that is kind of a painful thing now. We'll have to move away from that. We're doing more work in that direction. And a really important lesson is indirections aren't always bad. As performance engineers, we are taught that indirection adds performance overhead, right? And that is true, but sometimes it gives you leverage like this, which allows you to do very, very interesting things, right? These were the design alternatives we considered. You can look at the rigor of this whole thing in this slide. You can see how we kept how we tried to keep our intuition out of the picture and used like a data-driven method. The details are not important, but you can see these are the pivots that we were looking at, and these were the scores that we gave each of the potential designs on these pivots, and that's how we chose our favorite design. Right. The path list taken. The example of this is the SQL proxy running in shared memory with the semantic change stack, the whole thing that I talked about, the migrator, the label handlers, and so on, and doing all of this using a GNI bridge and running Scala in a JVM that's running a shared memory with SQL proxy. And had things not gone well, we had a choice. We would have fallen back to running it as a separate process and using gRPC, right? So this gave us a lot less overhead, right? It allowed using protobuf to serialize complex data structures, allowed us to avoid unnecessary GNI bridge traversals for things like, hey, what is the value of this string? What is the value of that integer? What is the value of that long? And so on, right? So the bridge traversals were avoided, and there's only one bridge traversal that happens for a select call downward, and then for reading the rows upwards, and there are no other traversals, right? Um, and this can be separated into a dedicated service if we hit a roadblock, right? So yeah, so that's what I'm going to leave you with, and thanks a lot for attending.
Hi, JJ. Can you hear me? Thanks for the session. I think it's surreal how the challenges you talked about overlapped with our previous talk. Not sure you saw it, but I think it revolved around metadata consistency when we are doing some major upgrades. Anyhow, I think we have one question from Munish. What was the design issue that you saw with respect to consistency? Was it read or write amplification? And was that an issue to get stronger consistency levels?
Well, there wasn't one. There were multiple. There were the more than 10 or 12 things that were fundamentally broken. One of them being, say, a node goes in a network partition for some time, and then it comes back. And what should happen to the rows that are stored on that node, the shards that are stored in that node? Uh, what should happen to the state of the rows there, right? If you don't wipe it all clean and bring it back, then there's a chance that the old state of the rows would resurrect. So if you have deleted any rows in the cluster in the meantime, and then the network partition heals and the node comes back, the rows will come back along with it, right? So every component had to write a GC for themselves. So file system had a GC logic. Happy has a piece of GC logic inside it that says if I find a file that does not have a parent pointer or doesn't have valid parent pointer, that means we have done a recursive delete and we must delete that row. Why? Because Cassandra will bring it back, right? So there were issues like this. If the clock jumps forward, the update would be issued with the latest time of the clock. And then if you try to issue if the clock jumps back by just a second or just a few milliseconds, then the next select would read the next update would go under the previous update. So the old update would win over the new update, right? This is broken at a very fundamental level, right? So these are the kind of things that we were facing with Cassandra, and there were multiple of these.
Cool. Thanks, JJ.